Welcome to homework.
Okay, so in this problem we have a potential energy described by U that is equal 1/2 of k x square plus y square plus z square. And in the first item we have to show that the wave function psi equals psi x of x that multiplies psi y of y psi z of z is in fact a solution for the time independent Schrodinger equation. Okay, so let's remember here what is the time independent Schrodinger's equation. So it's just a negative Planck constant square to m that multiplies d dx plus d dy plus d oops dz applied to the wave function psi plus u psi that is equal the energy psi. So we just need to show that this is in fact a solution and then describe the energies. Okay, so how we going to do this? Well, it's pretty simple. Let's simply apply the psi, which is this guy in here, and substitute in each one of these components here, of these terms in here. So after doing this, we will get an expression that is huge. So let's just write the expression here. So we have negative h to m d psi x dx plus 1/2 k x squared psi x that multiplies psi z and psi y. And we must repeat this for all the three components. So this is going to be plus negative 2m d psi y divided by dy plus 1/2 of k y squared psi y psi x psi z, and finally the last one h2 to m d psi z dz plus 1/2 of k z squared psi z psi x psi y. Okay, so this huge equation here is the Schrodinger equation, just the left side. Okay, I'm not considering the side of the energy, so the left side. And as we can see, we have in here three terms, three equations inside the parentheses. Okay, therefore we can attribute that each one of them is going to be equal some defined energy, which is Ez psi z, Ey psi y, and finally Ex psi x. Okay, therefore this is the entire Schrodinger equation. So here is how we prove that this function psi here, generic function, is in fact a solution of the time-independent Schrödinger's equation. Okay, because we can simply describe this solution as being negative H2 2m. This is the Laplacian, which is the operator written in a simplified way, applied to the psi, plus u psi, that is equal the sum of all the energies, which is Ex plus Ey plus Ez applied to psi. So that is the answer. This is how we show that that wave function is in fact a solution of the time-independent Schrödinger's equation. Okay, so this is the first thing we need to do. Now let's move on, and we just need to answer what is the associated energies of this solution. So we just want to describe who is each one of these is in here. Okay, how are we going to do this? The problem already gives us the tip. The problem states that the energy for the one-dimensional harmonic oscillator is described by n plus 1/2 of h omega. Therefore, we're going to have one energy of this type for each one of the dimensions. Okay, because this is a three-dimensional harmonic oscillator. Therefore, our energy that we're gonna call x, y, and z is the total energy, which is the sum of these energies here. Let's put here Ex plus Ey plus Ez is going to be basically Nx plus Ny plus Nz plus 3/2 because we have 1/2 for each dimension that multiplies h times the frequency. Okay, so that's the answer for the energy. And finally, the last thing we need to do is to calculate uh, the energy of the ground level. And for the first excited state, so let's move on. Knowing that this is the general form of the energy for the ground state is going to be E000, which is the ground state. Therefore, we're going to have 3/2 of h omega. So this is the energy, and this is the only possible combination of quantum numbers that describe this energy, because it's the ground state energy. Now, for the first excited state, we have E100, or we could have E010 or 001. All these three configurations give the same energy, therefore we have a degeneracy here, and the absolute value of the energy is 5/2 of h omega. So this is the energy of the first excited state, which could be described by any one of these three combinations here. Okay, so that's the final answer. Thanks for watching.